lecture will be in the second week, and then the availability of the lectures and things like that, we have to shift it to the third week. And so what I will today talk about is the nuclear shell model, but I inserted a word which I think is important. This is the solvent. Shell model. So what do I mean by that? Is that I will not give lectures on the shell model in general, because that would be, that actually would be in itself, it would be a 3-week course. So we decided not to do that. What I would like to do today is to show that the techniques that were introduced in the first week and that were used in the second week, in particular by Jan Jory and by Norbert Piet Lectures, that these were in the context of the IBM. We talked about IBM 1, IBM 2, and IBM and symmetries, and how you can classify states by symmetries. These same techniques, they can be used in the shell model. Okay, so this is, in one sentence, the goal of this morning's lecture. And this goes back to some old models, and they're listed here. And this is actually the menu for this morning. So I will talk about pairing. This will be again discussed by Augusto, but Augusto will do more phenomenology and applications of pairing. What I would like to do here is pairing from the point of view of symmetries, how you can use the technique that was introduced previously in order to solve a pairing problem. Then I would like to discuss SU3. So this was also already mentioned by Carpio. So now I would like to give a derivation of Elliott's SU3 model. And actually, to do so, it is necessary to discuss a very old model, which is known as SU4 for supermultipleting. So this is sort of something you have to discuss before you can attack SU3. Okay, so pairing. There are many versions of pairing and many symmetries depending on the situation, and I would like to start with the most simplest situation, where you take a single shell, I will say single J shell, and I will take identical particles. Okay. Now, for a single, this was just to remind you, we had a Hamiltonian. I will do the derivation in second quantization. So we had a Hamiltonian, which looks like the single particle energies and then creation and annihilation operators. So this is, and then there is two-body interaction. So I will stop at two-body interaction, and this now we want to write in coupled notation. So this is a sort of a very general notation, and I don't worry about angular momentum. So now I want to write this in coupled notation. How do you do that? So the alpha for the single J shell, this becomes J, it's always the same J, and then the sub-index Q. So for remind you, alpha was running over all available single particle states, right? And the same with alpha, beta, beta. Okay, so now you have creation and annihilation operators that have the indices Jn. Okay, same thing. Okay. So then, in second quantization, this Hamiltonian can be written as 2J plus 1. You couple two particles to unknown to 0, plus then there is a factor, there are some signs you have to be careful about. If I'm not mistaken, this I will go a bit more, I will explain what this is in a moment. Okay, and then the annihilation operators. And this is coupled to 0. Because the Hamiltonian is a scalar, this is something we impose. We want to have an interaction that preserves rotational, that is rotational invariant. And so then we need to construct a scalar Hamiltonian. So what is all this? Well, one thing I have to explain, this was also already mentioned by Jan Joly, I believe. You have these tildes over the operators, and this is just to make it a spherical tensor, so minus 1 to the J minus M. And I will follow this convention. Some people, like Jan, follow the convention here with a minus sign. This is just an overall sign in the operator, so it's a matter of convention, but you have to stick to this convention. And I believe our model uses the other convention as well, so this will be important this afternoon. To get the sign right, you have to remember these phase conventions. Okay, so this is the definition of this tilde operator, and then we have a one body, so these coefficients, so this is my single particle energy, and these are my two-body matrix elements coupled to J. Okay, so this is just a number operator if you write this out. Put in the Clebsch-Gordan coefficient, so this is with Clebsch-Gordan coefficients coupled to 0. What you will find is a sum over m, beta Jm, Ajm. Right? In my convention of the definition of the tilde operator, this is just the number operator. Okay, I will sometimes put a hat here to show, to indicate that this is an operator. Okay. So this is the number, it counts the number of particles in the shell. Total number of particles. Okay. These are the two body matrix elements. So remember a two particle state. It will now be invited in second quantization as follows. So you create two particles, you couple them to J with projection N, and you act on the vacuum. So this is a two particle state. Okay. And let's write this in sort of a compact form as J squared. Right, so you have two particles coupled to J with projection N. Okay.
Excuse me.
Yes.
Now we consider only even system.
No,
No.
it can be an odd system too. And so in the exercises we will do both even and odd. But they are identical and they are in the same J shape. Okay? I will come to the generalizations, not neutrons, protons, evolutions at the end. of this model. Well, the first half of the model. Okay, so this is the definition of my two particle states. So let's say that this is V1, maybe that's not a good notation, but this is the one body term, this is the two body term, okay, for two, these are operators. I should put a hat. Okay, so this is the definition, then we can show that these coefficients J are precisely the two-body matrix elements. So these are normalized states, and if I sandwich, and you do the second quantization formalism, if I sandwich this interaction with the minus sign and the 1/2, oh, I've forgotten the factor, it's 2J plus 1. Let me check. Yes. Okay, so you need to put all those factors in, you calculate the matrix elements, what you find precisely, the matrix element of this interaction as defined as such is Vj. Okay? So the interpretation of these coefficients, these are the two-body matrix elements. And actually, the interaction is completely specified if you choose a set of matrix elements here. And remember, this J, if the particles are identical and in the same shell, this J can only be even. Okay. It's already a week ago, but it's still valid. Okay. So this is a general Hamiltonian for a single J shell. Now, what is the pairing interaction? The pairing interaction. So let me make one point before I come to the pairing interaction. I can right now H, the H that I put there, so it is one body term and two body interaction. So this is now just 2 epsilon j plus the two body matrix. Right? Everybody agrees with that. You have two particles, you count the number of particles. Each particle has a single particle energy of epsilon j. And then you have a two body interaction, which is characterized by this. Right? Okay, so now I want to do this for n particles, because I'm interested in the many body problem. N particles will have additional quantum numbers. I don't know them yet. This will be part of the discussion. For V1, this is easy. Right? Because it's just n times the single particle energy. Right? This is, I hope everybody agrees with that, so that's easy. Question is, can I find an expression V2? Right. Are there two body interactions where I have a closed expression of an analytic understanding of the n-body wave function? And this is where the pairing interaction comes in. The pairing interaction is defined as such, so you have this where, so this is pairing. And let me give it a subscript, superscript P. That is for information. G this is the strength of the pairing interaction. In nuclear physics, this pairing interaction is attractive. So the G here is positive, and this makes the matrix negative. And then this factor 1/2 2J plus 1, this is some conventional factor. The essential check is, well, I need of course to have J is 0 and J. And that's a very simple interaction. So this to give you an idea. And again, this is the spectrum we discussed a week ago. Letter 10, it's two particles in the G9/2. This is the spectrum of the delta interaction. The pairing interaction is yet a further approximation, so you just separate out the 0 plus from all the other angular momentum states. Okay. It's an approximation, of course. So why do you make it? Well, you make it because, as I will show, I will find a closed expression for the n-body if V2 is the pair. Then I will find modulus. And so now I will spend some time giving you an idea of how this problem can be solved with the techniques that we saw the previous weeks. Clear? Okay. Okay, the first thing we did, if you remember, was to construct operators like creation, annihilation. So this now, in our case, single J shell identical particles, so this will become something like that. The J is the same, but the M's can be different. Okay. So these were the operators that formed an algebra, which is U omega in general, and so in this case we have 2J plus 1 quantum states, different quantum states, so it's U 2J plus. Okay. And so I can take linear combinations of these operators with the Gordon coefficient, so I can replace actually, and you still have the same algebra, something which I will call operators in lambda with projection U, and then I couple them to angular momentum lambda. Okay. So this is just a linear combination of that, it forms the same algebra. You can take linear combinations of generators, you don't change them. So these operators, they also form this algebra, the same algebra. So now, this was already shown by Jan. You're interested in commutators. These generators. So this will be a sum over 1. Then we have Gordon coefficients. Then we have phase, which is this. just correct this. Yes.
Is the Plectures right? Isn't it like the second?
The second is a double. Okay, this is just computing, right? So this is. But then you see here, this is the important thing. Let's suppose that lambda. This was a point which was also made by Jan in one of his discussions, right? So let's suppose that this one is odd, that one is odd. The lambda here, I should mention, the lambda goes from 0, 1 to j plus 1. All the angular momenta are allowed, because this is creation and annihilation. If you have creation, then only the even angular momenta are allowed by anticipating. Yes. Okay. And you can show, you can convince yourself if you do the sum of these. If you do the sum of these angular momenta, you get the same number of generators, namely 2j plus 1 squared. This is the number of generators of this algebra. Okay, so now you say I take lambda and lambda prime on. Okay, then this is even, and then the only existing one is an odd one. So that implies that you have a sum over lambda double on. In other words, what I'm saying is that you have a set of generators. This is 1, 3, and so on, to j. And this closes on the commutation. The other point is the angular momentum. The angular momentum operator is just A1 or proportional to A1. Okay, so this is proportional to This is because the angular momentum operator has to be a vector, a tensor with 3 components. And so the only one which is contained in this algebra is A diagonal J, AJ equal to 1. So what we have done now, we started, remember our terminology, we had a dynamical algebra, because in this case it is 2J plus 1. We wanted to go in some way to a symmetry algebra, which is SU2. The angular momentum I should put here J. This is the notation. This is the total angular momentum. And what we have identified is an intermediate algebra. This is all the operators A lambda for any value of lambda allowed by the problem. And here in between we have an algebra which closes, and this is the symplectic algebra. Never mind the name. It's the algebra which is formed by the odd angular momentum, the odd lambda operators A lambda. Okay. Yes.
Does it say A mu epsilon j in the last? I can't read the symbol.
Where is it?
It's you.
This one?
This one. Yeah.
It's 2j.
2j. Okay.
2j. So it's the maximum angular momentum you can obtain by coupling two objects with angular momentum j. Right? And this is odd, but it's allowed because this is creation, this is annihilation. And so this is what we wanted actually. We have a dynamical algebra, we have a symmetry algebra, notations, and we have identified in between them an algebra which is the symplectic, actually it's the unitary symplectic, but never mind. Never mind the name, it's the algebra which is formed by these operators. And so now we can we can apply our procedure that we did previously, because this Casimir operator, this algebra has a Casimir operator. The Casimir operator can be expressed in this operator, and this is just A daggers and A tildes, and we can rewrite these Casimir operators in terms of interactions, two-body interactions, which I already erased, A dagger, A dagger, A. Okay. So this is what we're looking at, because this will be a solvable Hamiltonian. Okay. I will not do the derivation, right, because the procedure is now clear. We have to identify the Casimir operator, and then we have to find the connection of this Casimir operator with the interactions that I wrote down. There is a much simpler way of doing things, which I will explain in a moment. Just the Casimir here, the Casimir operator here, in this case, will be something like might be a factor. This is on. It's quite logical if you think about it. What is the Casimir operator of SU2? It is J dot J, okay, which if I write it in terms of this A, so it's A1 dotted with A1. I mean, if I want to write this explicitly, it's a sum of nu. A1 nu. Nu. Okay. This is the definition of scalar product. So this is the Casimir operator of SU2, and the Casimir operator of symplectic 2J plus 1 is simply the generalization that you take a dot product for all the components. Okay. And then there is a very lengthy derivation, which I will not do, where you can show that this guy can be related to the pairing interaction that I was mentioning previously here. This because you have to recouple and that's I gave up on it in my notes, and I did it in a different way. In this different way it's much more elegant, and actually it is something that can be used if you go to complex situations where you have neutrons, protons, separation, and so on.
So I have a question. So you first of all write your Hamiltonian as V1 and V2, so the single body interaction and the two body interaction, and then you introduce the parent interaction. If you have if you sum over pairing interaction, would you get again the V2, or it's just some part of the two body interaction is pairing interaction?
It's part of the two body interaction. So the entire V2 it is specified by all those matrix elements, and J goes from 0 to 2J minus 1, okay, even. Okay. All those matrix elements or those numbers specify the interaction. What you do for the pairing interaction, you say they're all 0 except 1. take different from 0 is angular momentum J equal to 0. So that's the definition of the variable. So of course, it's not a general interaction, it's just a specific interaction. Now
So you say, okay, let's just couple it to 0 and forget the...
yes, forget about, in practical terms, what does it mean? Right? I have my spectrum here, I can take a delta interaction, I don't even take a delta interaction, I just take, I have 0 plus, and then all the other states, they are 0, they don't interact.
And then just J, so
Yes,
0,
just,
0.
this is just one attractive matrix. In nuclear physics, it's attractive. Actually, in the first application, it was repulsive. I will say a little bit about the history of pairing in a moment. Okay, so let me now introduce, so this, I sketched here the way to do it, Casimir-generator expression in terms of the generators, and then trying to connect it to the pairing. Fine. You can do it in a better way. This is called quasi-spin. Formalism. Okay, what you can do is to write this pairing interaction in second quantization. If I'm not mistaken, this is not. There's no 2J plus 1. Okay, I just take one component of it. Let's see, this is minus. Let me check. Okay, now if you remember, we introduced this guy and we called it 1/2 2J plus 1 G. Right, this was our convention. So you put that in with plus 1/4. I put these factors because they could be important this afternoon. You need to get the signs and the factors right, because otherwise you will get the analytic solution. Okay. Okay. Now, what you can define now are pair creation operators and amplification operators. So this is the square root of J plus 1 of the pair coupled momentum 0. This is an S pair. It's precisely the pair Jan and Jolie was talking about, but now it's confined to one single orbit. Okay, so there is only one choice. It's just coupling two particles to angular momentum 0. Then there is the Hermitian conjugate operator, S minus, is just the Hermitian conjugate of S plus. Okay. Then you can do the trick, you take the commutator of S plus and S minus, and you find test my memory. This is in my notation. Okay, this is what you find. This now you can call, you see it coming, you can call an operator 2SZ. Okay, we call this combination 2SZ. Then you can also look at the commutator of SZ plus or minus, and what you will find is plus or minus. See that neat? So we define pair creation operators, annihilation. We take the commutator, it gives us a third operator. If we compute that third operator again with s plus and s minus, we find these operators again. So we have an algebra. The algebra consists of sz, s plus, and s minus. And this is, I don't know, this is an SU2 algebra, and this quasi-spin algebra. The name now is clear because it's like a spin algebra, it's the same commutation relation, but it has a different interpretation, as I will show in a moment. Because now the derivation so let me replace this. This actually you can show it's minus u. So there is actually this s minus is minus. You have to be careful with signs. So you put that in, and you find that the pairing interaction is just this combination s plus s minus, and the s plus s minus they form together with the set across algebra. And so now the derivations are easy. This is just using these commutation relations in order to get that expression. Now the thing is done because we know that this Hamiltonian here will be labeled by this classification. So we have SU2. Maybe Q quasi-spin, but with agitation. Okay, so this was consisting of SZ S plus minus, reduce it to SO2, which is just SZ. This Hamiltonian will be diagonal in this basis because it's just a combination of the Casimir operator of this one, which is s squared, and then some just a single operator associated with that. And so you know that your states will be labeled by a quantum number S and a quantum number ms. Okay, the projection of the quasi-spin. So I can write yes. I should maybe put in other quantum numbers here, which I don't specify at the moment. So this will be minus g. And I put here ss plus 1. This is the eigenvalue s squared minus ms plus 1. That's the solution. Of course, we don't know yet what does this ms and this s mean. Right? What is the physical meaning of that? One is easy, because we had an expression here for sz. The eigenvalue of sz is ms, right? And eigenvalue here is 2ms, so immediately. So what I am saying here, basically ms is equivalent with particle number n. Okay. Now I will do a similar equivalence for s, and I will call it 1/2 2j minus 2v. I will discuss that in a moment. This is again, it's just a definition. No? It's not. Okay. So this quantum number s, we still don't know what it is. It's equivalent with v. And I can tell you now immediately this is seniority. This is called seniority, and I will explain a little bit why this is called seniority.
So just to
Yes.
double check, this V has nothing to do with the interaction strength, right?
No, yeah, this is an unfortunate the interaction strengths are labeled with V index J, the spin. And okay, this is what I've always done, but seniority conventionally it's labeled by this. This is actually, it derives from Raka introduced this, and in Hebrew seniority is vetek. That's the only word in Hebrew I know, but and so I will explain how seniority comes into this business. And so that's why it's always labeled by V. Okay. Yes. I can rewrite this in terms of my n and v, and what will come out is n minus v. This is 2j minus this is just, you have these relations, I can put it in terms of S, I have it in terms of S and ms, I can put it in terms of particle number, and say, okay. So immediately what you see now is that S minus, this is this one, let's act now. And I will write the state alpha s. I can now write it as so I had states, eigenstates like this. So I now will write them in a way which is familiar. So j to be n, because ms is equivalent to n. There is still an additional point, well, a possible additional point alpha. Then V seniority, and the alpha here, we put this interaction is rotational invariant, so it is also labeled by angular momentum and projection. So in principle I should have put that here also. Okay. And so now I want to tell you something about the seniority. What are the properties? So let's add to S minus in this state. the seniority equals the particle number, then this interaction gives 0, and the only way that can happen is if S minus acting on the state is 0. And this gives you the physical interpretation of seniority. If I have a state with particle number equal to the seniority, then none of the particles is in pairs coupled to 0. This is sort of the intuitive understanding of seniority. Another, I want now to construct a state with n particles and arbitrary seniority. How do I do it? Very simple. I take S plus, I act with it. Well, this is not normal. This should be proportional to, and I act with it on here you just add pairs of particles coupled to 0, so you don't change the number of particles which are not in pairs of particles coupled to 0, so the seniority remains the same. Each pair creation operator adds 2 particles, so you go from V, acting n minus V over 2, to n particles. So this is sort of the parent state, or the senior state, because from this state with equal particle numbers equal to seniority, you can generate the whole series. That's the idea. That's why I can call it seniority. Okay, and so this is a much simpler derivation than in terms of symplectic algebras, because all the properties can be derived from properties of SU. These we know very well. Okay? So, a little bit about the history of this thing. So this was introduced by Raka. Raka wrote a series of 4 papers in the 1940s, and these were all called Theory of Complex Spectra. These were sort of important papers. I mean, like Physical Review selected in 2000, it selected 100 important papers of the 20th century. So to get into that league, you have to be good and write nice papers. And one of the papers of this series was selected, was in this 100 series. So this is the third one. And this is where Raka introduced seniority. And amazingly, he doesn't say anything about it in the abstract. It's a paper that he discusses fractional parentage coefficients, which I hope you remember. Okay, and he developed, these CFPs were known at that time, but he really developed the techniques to calculate them.
But this paper is also interesting, like, first of all, when it's wrote 43.
Yes.
And also, you're still in Palestine.
Palestine.
Yeah.
Yes.
It's
So
just
still Palestine.
very interesting paper.
Raka was Jewish, and he escaped. He was Italian, Jewish, and he escaped Italy in the 30s. He went to work in Palestine, although he had offers for Princeton and wherever that he wanted to go. So, it's a paper about atomic spectra. This is not nuclear physics. And so he classifies electrons in atomic configurations. And so, amazingly, so he introduces this is taken from this paper, you see. He introduces an interaction, so this is now orbital angular momentum, because in atoms you do everything in LS coupling, so you couple the particles, the electrons, in orbital angular momentum. And so he defines an interaction which is precisely what I wrote down, so this is very much related to that. Okay? And he finds the eigenvalue which is almost identical to what we have here. There is some difference in the 2J's and the 4L's because you have spins and this is integer. Here it is not integer. And he also talks about the seniority number. And this is sort of a strange thing to do because the pairing interaction is not at all a good approximation, because the electrons, of course, they interact by Coulomb. It's repulsive. Okay? And the repulsive interaction will put actually the seniority, the lowest seniority states, at high energy. Whereas here, if you look, G is positive. Remember, for an attractive pairing interaction, G is positive, and then the biggest eigenvalue you will obtain, or the lowest eigenvalue, I should say, the lowest eigenvalue you will obtain if the seniority is 0 or 1 for an odd mass particle. Okay, so the low seniority states are at low energy, and that is much more useful actually than in the atomic case where you have a repulsive. So this, although it is not a good approximation to the Coulomb interaction, Raka used it to classify states. It's a classification. And actually, for instance, the program you're using, Archmodel, it uses a seniority basis in order to calculate the coefficients of fraction parameters. And this is based on this Raka's technique. Okay. So, a little bit of history. So this I discussed, so this is a repeat of what I said. So these are this is perhaps worth to mention, to stress the analogy between the bosons with spin J, so then the J will be integer, and then the seniority is associated with an orthogonal group. In the case of fermions, then the J is half odd integer, and then so this is the generators with odd angular momentum. They form a symplectic algebra, and so the two are very much equivalent. Actually, this was also pointed out by Raka a bit later in 49. There is a generalization, I will not go into that, because it becomes very useful, much more difficult if you go to, for instance, neutrons and protons, then you have an intrinsic label, T, and so then your total dimension here, right, is not 2J plus 1, but is the multiplication of the generalization, 2J plus 1, 2T plus 1. Okay, you can have a classification. This was also done by Raka, and at the same time by Flowers. Lord Flowers, he became Lord later. He made a nice career. Okay, so now a little bit about these quasi-spin algebras. Why are they so interesting? Because the generalization now to several degenerate shells is rather easy. So what I did so far was just taking a pair of particles in a single J shell. Now you can define operators just as sum over the orbits you want to consider. So this is a problem now that becomes familiar. So you have a number of orbits. This could be the thin isotopes. So you have 50 to 82. Okay, so you have neutrons. And they are in B5 G7 H 11 nuclear. Something like that. Okay. So you have 5 different orbits, each with its J, and the approximation now you make, I will go to the non-degenerate case, but the degenerate case is really easy if you say, well, the spacing between these levels is small, right? And it is small compared with the strength of the interaction G. Right? And so in the limit, you can say, well, I have a set of degenerate orbits, completely degenerate, in a pairing interaction. And this problem is solvable, and it is solvable in an identical way. This is what I showed. It is solvable based on commutation relations, so you take S plus S minus. Right? So now this is the number operator, and this omega is just the sum of 2J plus 1 over all the J's. Right? So the omega in this case will be 32. Okay, the degeneracy of relations. And you can apply the same sort of derivation to get to a closed formula for the energy. And in terms of seniority, particle number, and then the degeneracy of the shell, 2J plus 1 will be replaced by this formula. And we have again a closed expression. There is one thing we should mention, and this is the structure of the ground state. Let's look now at an even nucleus. Okay, and I don't know whether I erased it. No, it's still there. So, as I said, the ground state, an even nucleus, the state with lowest energy will have seniority 0. Right? Because this is positive, the minus sign. This is positive. Okay, so what will be the ground state? It will be the ground state. Of an even nucleus. Let me forget about this alpha because it's not needed. The seniority is 0. Then one can convince oneself that the angular momentum of that state should be 0 also. That's quite natural because you have only pairs of particles coupled to 0 in any state. Because this is now S plus n over 2. Because this will be a state without any particles. And this is actually the exact ground state of a pairing interaction. And it still works in this quasi-spin approximation, but in this approximation of degenerate orbits. So then this S plus will be just the sum G of pairs of particles coupled to 0 and sitting in the different orbits J. Okay. That's quite, I mean, this is sort of, it has connections with BCS, it has, some people make connection with superfluidity because you have like identical object. This is an object with bosonic properties, it's a pair of particles. So you have identical objects, n over 2 of them, and that makes them the ground state. So this is the idea of a condensate solid state. Okay. So, the interpretation of the SU2 labels that we did. Then there are some generalizations. Maybe Augusto will talk about these things, I don't know. But this is let's say the power of quasi-spin actually becomes more quasi-spin becomes more powerful if you go to neutrons and protons, and if you go to neutrons and protons with two types of pairing interaction. And so certainly Augusto, he will discuss the case where you have neutrons and protons interacting by isoscalar and isovector pairing. You can also discuss it in algebraic ways. He will also discuss evidence of nucleus opportunity, so I will not spend too much time. So one thing which is obvious in this is so that the first indication of this idea of seniority is that if you take this expression for the energy, which is here, then so the ground state, as I said, has seniority 0. The first any excited state, right? The first excited states, they have all seniority 2. And in particular, the 2 plus 1 has seniority 2. You just take the difference between seniority 0 and seniority 2, you get something which is a constant. So the prediction is that even if you vary the number of particles, right, and this is the example of the tin isotope, so you vary between 50 and 82 the number of particles, see, the prediction of a simple seniority scheme is that the energy of the first excited 2 plus should be constant. Right, and this is more or less followed. This, of course, is an exception because it's a doubly magic nucleus, so there are no particles to excite, except you have to break the shell closure, and so then you get an excited state at much higher. So let me do one more thing before the coffee break. And this has to do with conservation of seniority. Okay, so I hope I convinced you that if I take a pairing interaction, I will have eigenstates which are classified by not only by angular momentum and projection, of course particle number, but also by the seniority quantum. Okay. Now the pairing interaction, this is a good approximation to any interaction we want to use in a nucleus. So the question is now, and this was extensively studied by the students of Raqqa, in particular by the Shalit and Talbi. The question is now, well, what happens if I take a general interaction? Right? Any interaction which is specified by these numbers Bj, right? So pairing interaction with A equals to 0, but now I take all of these numbers, 2j minus 1, right? In principle they can be non-zero, but they will be non-zero in an actually realistic interaction. What about seniority? Is seniority a good quantum number, or is seniority broken? this is indicated here. I will say some things about it because the derivation is quite interesting. And you can derive precise conditions for the conservation of seniority of a given two-body interaction, still in a simulation. Right? I'm still in a single. I go back to a simulation, and I will indicate more or less how you can do that because it involves CFPs, and this we discussed in the first lecture. What is the conclusion? The conclusion is rather amazing. That whatever interaction you take, you consider between identical fermions in a shell with spin J, all the states will conserve seniority if the J is lower than or equal to 7 halves. This is, it has to do with the exercise you did on the first day, where you looked at the wave functions of a state in a 7 half shell, and these peculiar properties you find that you could only construct one state with angular momentum 7 halves for 3 particles. You can have a similar statement for bosons. This is sort of interesting. This is Bose-Einstein condensate. And here the statement is that any interaction between identical bosons with spin J, so the J is integer here, and it conserves seniority if the J is 0, 1, or 2. So there are lots of Bose-Einstein condensates where the atoms have spin 2, I spin 2. Okay. These can be solved analytically for any interaction. Yes.
How do we, sometimes because this seniority number is a little bit abstract, so it could not be measured directly in an experiment. What do? We do use some selection rules, or do we use?
It is with selection rules, and in particular, I have a nice case of selection rules in one particle transfer reaction, where you have, for instance, well, this is going ahead a little bit, but maybe I will tell you. So you have a system, for instance, let's say J equals 9 half. Okay. So you have a nucleus where you have a J to the 3rd configuration. So this would be 9 half ground state. The ground state will have seniority 1, and the spin will be 9 half, let's take 3 9 halves, so the spin will be plus. Then you transfer to a nucleus which has 4 particles, right? So this will be even spins, the ground state will be 0 plus, but there will be, this will be seniority 1. There will be, for instance, if I remember correctly, 4 pluses. 1 has seniority 2, so this is seniority 0. Right? This is always the lowest. This is seniority 2, this is seniority 4. Now one can show that in a particle transfer reaction, you can change the seniority, one nuclear transfer, you can change the seniority only by 1. So, you can go to this one, and this one is forbidden. So that this would be a case where the seniority, but it's not a direct measurement, it's a measurement by selection. Okay. Now, the problem is, of course, that you want to have those 4 pluses close in energy, right? But if they're close in energy, seniority in this shell, it will not be exactly conserved, so there might be still mixing, and then if the 2 mix, then of course this picture. But there is a case actually where you have a solvable state, where this state, whatever interaction you take in a J equals 9 half shell, it will not mix with that 4 plus. There the selection rule should hold. I'm trying to convince my experimental colleagues to do such an experiment, but so far we've not succeeded, because apparently this is, I mean, the cases that are feasible, they're very different, so I don't see a way to do it. But this would be a very nice, actually, direct indication of the existence of singularity. Okay. It's difficult. Okay, so now, let me get back to this conditions on the conservation of singularity.
Excuse me.
Yes.
I want to confirm this situation. V equal 1 is all particle coupled pair.
Yes,
And
except one.
except one.
Yes. Because so V is the number of particles not in pairs coupled to zero.
Not
Yes.
so V equal 2 is only 2 particles.
Yes. In a different terminology, they would call this a broken pairs.
A broken one pair.
Yes, one pair. V equals 4 is broken 2 pairs. And it's sort of, yeah, you can see this selection rule, it's logical, right? Because you have here a pair coupled to 0, okay, you can easily go to 1 pair coupled to 2, but to 2 pairs coupled to angular momentum 4 in total, but to 2 broken pairs is more difficult. And there is actually the exact solution.
I see.
It would be nice to have I agree, a direct measurement of quantum numbers. But this is a similar question which was asked about sigma in the O6 limit. There is no, you can derive it from selection.
Same goes with some isospin selection also. There is no way we can measure.
Yeah, isospin, I guess, is the same story. You have selection rules based on isospin, but there is not something like angular momentum where you can measure the spin, well, the angular momentum of this thing. Okay, let me say a few words about this, how we get to this amazing statement. And this is actually by studying the 3-particle system. So a 3-particle system, and now I will go back a little bit to what I said in the first lecture. I hope you will remember. So, how can we construct a singularity one state? The angular momentum necessarily, so this is the total angular momentum, this is the angular momentum of the shell. I look at singularity. And so, this is now in the language of what I introduced. If you remember, I introduced these brackets. I put in an intermediate state. And this is, if you remember, this was a notation. We started out with 2 particles coupled to 0, coupled to a 3rd particle. It's not antisymmetric, we antisymmetrize, and this is the resulting state. Okay? And this is precisely singularity 1, because we started from a pair of particles coupled to 0. Okay? So now, what is a singularity 3 state? With the same angular momentum. Okay. So it is any angular momentum different from 0 this time. So we start from a pair of particles coupled not to 0, any other angular momentum. Okay. And the final copy is to J again. Okay, so that is the naive definition of a singularity 3 state. Unfortunately, this is wrong, because these 2 states, as we saw in exercises, these 2 states are not orthogonal. So you have to orthogonalize them. How do you do that? So j prime here is different from 0. Okay. And then I have here again. Yes. I just subtract a component. This is like a Gram-Schmidt normalization. I orthogonalize explicitly this state to the singularity state. Okay, now, how do I get my conditions? This is a necessary condition for an interaction to conserve seniority, is to say, well, I have a senior constructed the seniority 1 state, J. I have any interaction, two-body interaction, and I want that it does not mix with the seniority 3 state. This must be 0. Okay. This will be a necessary condition. This is an example where you say, I see two states, they are classified by seniority. I impose the condition that the interaction does not mix the two states. So that is a necessary condition for this interaction to be seniority conserving. You can also show that it's sufficient. This I will not do here, but you can, once this condition is satisfied, you can convince yourself that the interaction conserves seniority for all states. And now, the only thing we want to do is to calculate, this we discussed in detail in the first lecture, how to calculate two-body matrix elements between three particle states, right, in this kind of basis, right, with intermediate unknown momentum. So we have the whole machinery to derive the condition that this thing is 0. This condition is written right. This I want to repeat because transparency is this Vj is so remember, these are the two-body interaction matrix elements. And these are just numerical configuration. So we find a linear combination of the two-body matrix elements should be 0. The amazing thing is now, and this is related to one of these exercises on the first day, is that if you put here j equals 7 halves, all those coefficients are 0. So any two-body matrix element will conserve 0. This is the same thing actually. Here I did it, you can do the same thing for bosons actually. So the sigma is -1 for fermions, I come back to this formula, and for it is +1 for bosons. the summation is over non-zero even values of J prime. So we made a mistake in my notes. No. It's J. Because the summation is over all the two-body matrix elements here. The J prime, you can choose. The only condition is it should be different from J. Even and different from J. Okay. So now, let me say, how does that work now? This is again the case we did. Right? So you have the two-body matrix, and which you can read off the spectrum, for instance, or you calculate in any other way you wish from a schematic interaction. Okay, this we will do in the exercise. You work out these coefficients, putting J equals 9½ in this case, because this is the value of the angular momentum of the shell in this case. So you have a sum over J being even and different from 0. So J equals 2, 4, 6, 8. This mu here is the same as V. Okay. These are the two-body matrix elements, two patterns coupled to 2, 4, 6, and 8. And then the only thing to do is to calculate this coefficient, and that is what you found. And so the condition for the interaction in the G9½ shell to conserve seniority is that this linear combination should be 0. If it is 0, it conserves seniority. And we will do some, like for instance, you can ask the question, what about the delta interaction? Okay, which we will do in the exercise this afternoon. Okay. Yes, I think I will stop here and then continue the discussion with non-degenerate orbits, non-degenerate orbits, and then I will go to the quadrupole relation. Yes, I think no, this is one. Yes, because this is a mistake. Yes, it's 2Z, which is 1/2. Yeah, correct. Because this is 2Z. So this Z is, yeah,
Yeah, or it should be 1/2, yeah.
only there.
There, yeah.
So these two
And then the other would be a
Yes, I wrote for the Z. This is 2 Z.
Yeah, it is this one. Yeah. And
No, here's 108.
Alpha j, and then you can solve the alpha j's up to a constant. You can solve the alpha j's from that. And the alpha j is proportional to g 1 over e epsilon j minus e. And then you put it back in, and you get an equation which looks like sum over j plus 1 half, and here 2 epsilon j minus e is 1 over g. Okay, this is two particles. In the notes you have a few more steps, intermediate steps, but it's basically simple algebraic manipulations. Okay, so these are the unknowns, right? So you want to solve this equation. G is, this is the strength of my interaction. So in nuclear physics, this will be a positive number. So it's an attractive pairing interaction. And so the epsilon j's, these are the single particle energies. Okay? And so you have to solve this equation. And this you can do graphically. Do it here. This is the graphic solution of this problem. So what you have on this axis is here the vertical lines, they correspond to the choices. I think it will be 2 epsilon twice the single particle energies. Okay, and then this blue curve here, this is just this quantity here, right, as a function of E, the energy. And so you want that this quantity equals 1 over G. And this line here is precisely G to the power minus 1. Now I have an attractive pairing interaction. So this comes back to the yes.
I don't understand. I think I don't understand why the particle number operator commutes with S plus.
The particle number
NJ, yeah?
yes. It does. It will not commute with S plus.
Yeah, and you said that this S plus operator commutes with the Hamiltonian.
Did I say that?
Yes.
Well, you've written it as
Yes,
an eigenstate. I think is the line he's concerned.
I think he said they have the same state.
This is an eigenstate of the Hamiltonian.
This is what you said. You didn't say it.
Yeah, and you said that this S plus commutes with the Hamiltonian.
It will not commute with the Hamiltonian. If I said that, then I've said something wrong. I think I've only said that this is an eigenstate of the Hamiltonian.
This, you said that.
Okay, maybe I misunderstood.
Whatever I said, I retracted. So it's not it's an eigenstate of the Hamiltonian, but it doesn't commute with it. Because you can see, right? Because this S plus, these are number operators, you create 2 particles. So, okay. Oh, I said you can write, yes, I agree. You can write it, the Hamiltonian, as a sum of commuting operators. This I said. But these operators are not the ones you see here, they're more complicated. So, and that, this derivation I will not do because that's a long. Okay, yes, so I understand your remark. So, you listened. Good. Okay. Right, so it can be written as a sum of commuting operators. So that's okay. Let me get back to this graphical solution. So it's 1 over G here. The G is positive for an attractive pairing interaction. And you see, if I increase the G, I will decrease this line, and there will be one state which goes low in energy. This is the same thing as Rick mentioned in the first week. This is the collective state. Right? And one can actually show that if this G in the limit of G going to infinity, that the coefficients of these collective states become essentially constants. And so you will get to a situation where these alpha J's become 1, right? And you get to the situation of quasi-spin. Yes.
That E equals 0 line, does this correspond to a bound state, or is the definition a little maybe different? I was just wondering if the equals 0 line looks like we're guaranteed to have a bound state in this interaction.
Oh, this can be shifted. You see, you can shift all those energies up and down with a constant, and it will not change anything to the problem.
Okay, that's
So,
what I was
but
curious.
essentially, I'm talking here about bound state problems. So no complex energies. And I guess in this example, I must have put the first energy here as at 0, but I could have put -1 on that, so it wouldn't change. The other point is that, for instance, if you now take a repulsive pairing interaction, so you go to the other side, you see that your collective state is not here. Your collective state actually gets here. It gets pushed up in energy. That is a property one has to keep in mind. For instance, giant resonances. They can be understood from that point of view. Okay. Now, this was for 2 particles. What do you have to do for n particles? Then you get an additional term, which it's 1 over G. And what is important that this is now for n of n. We can erase everything here. benign state of the Hamiltonian. This is quite strange equation. So you have your single particle energies. These are the unknowns, and so you have actually n particles, so you have n over 2 pairs. Okay, this is for an even for a system of even particles, we should say. So then you have an index that runs over the n over 2 pairs. Okay, and these are the single particle energies twice. And this is now a quantity which depends on the P. Right? So you don't have, remember that in the degenerate case you had a ground state which was of this type. Right? You had sum over J to the n minus 2. Okay? Acting on the ground state. What is replaced now is not identical pairs of particles, but with some kind of a factor. This factor we more or less understand from the two particle analysis. Okay. The only point is that here, I should say P, here we have now a more complicated equation. This was there in the two particle case. That was there, but now we have this term, which is additional, and which is sort of a repulsive. I don't know what is the interpretation, but this is an additional term which comes up in the many particle case. Okay, and these are called. This is called the Richardson. This will go down. Equation. Okay, these are nonlinear equations. You have to solve for the unknowns, right? EP, and then you have a solution of your pairing Hamiltonian.
So is this the result of what it means to be integrable?
Yes, yes.
Okay.
So the fact that you can write this by manipulating some fashion, by manipulating this as a sum of commuting operators, you can get to this result. It's not trivial. So this is. And what is nice, you can generalize this. You rely on the fact that you have quasi-spin algebras for each of the levels separately, okay, which are SU2. And then I showed you have something similar for neutrons and protons, which is SO5, or if you have more complicated pair interaction, SO8, and you can do the same analysis in those more complicated situations. So you have Richardson equations for a system of neutrons and protons with a pairing interaction, or a system with two different pairing interactions, T equals 0, T equals 1. These have been derived but not really studied in detail. Okay, so this is still not actually what you want to have, because this, as I said, this is a constant pairing interaction, right, between all levels, and you might want to do something a bit more tricky, which is this. That would be very nice if you can solve this case where you say J prime. I have pairing strings that depend on J and J prime, and then okay. So here you would have pairing strings that depend on where the two pairs are sitting. And you have actually, physically, you have a situation where if the two particles are sitting in the same orbit, you expect that this string will be larger than when you have a pair of particles here and a pair of particles. So it drops off. Right? And this, I don't know any analytic solution. What you can have is if it is separable, if you have jj prime equals a strength associated with OBJ times a strength associated with OBJ prime. This is a separate pairing interaction. And so there are some analytic solutions known for that. Okay, so this more or less is a brief sort of overview of more complicated pairing Hamiltonians. Okay. And this is still something where people derive new results. Like for instance this situation with neutrons and protons. Okay. The equations have been derived, but I don't think they have been studied in much detail. Let me now come to a last topic concerning pairing. This you also frequently encounter. People talk about pairing, and there is a lot of confusion concerning this. This is something which is called generalized seniority. Okay, and so I convinced you, I hope, that seniority is a quantum number which is conserved by the pairing interaction and by much more general interaction. But the general interaction actually is not solvable. It has the only property that the eigenstates, if it's conserved seniority, the eigenstates can be labeled with seniority. But it doesn't mean that you can solve analytically all the states. Okay? This now is a trick that was, or a situation that was proposed by Ptolemy 40 years ago. And let me put here a Hamiltonian, and he just, so this is GS is for generalized seniority. He just supposes that he has a linear combination S alpha, okay, which is an eigenstate of the generalized Hamiltonian. Okay. And then he assumes, in addition, a double commutator. To be he assumes those two properties. This is Ptolemy. In 1970. And this is not there is no algebraic structure related to this. Okay? But what you can show is that if these two properties are valid, this is, I still don't understand very well why this happens, but you have a solution which you can write, so n is 0 is defined here. So now you have to see the difference with Richardson solution. In the Richardson solution, you don't have this property because you have a superposition of n over 2 pairs, but the pairs are different. They're not identical. Okay? They depend on this factor here, the energy P changes from there to there. If you impose those two conditions, then you find that you have an eigenstate, and this is an exact result, it's not an approximation. The eigenstate of this Hamiltonian, whatever the conditions mean, is always the eigenstate with a constant structure, but not, I mean, this written explicitly, remember, it's sum over J, alpha J is plus J. Okay? So the alphas are not necessarily 1, as we have in degenerate orbits. No, they can be anything, but there should be a solution of this Hamiltonian. It must be a factor of 10, yes. Yes, and this there is now an approximation which is called the generalized seniority approximation. This is basically saying, well, I diagonalize my two-particle system, I find my coefficients alpha, and then I assume that this will be an eigenstate of my Hamiltonian. Right? Of course, if you want to be rigorous and exact, then you should check that your Hamiltonian satisfies this double computation. Yes.
Could you define this Hamiltonian or say what is it?
You can look at this paper and he derives the conditions. Why? What are the conditions on the interaction? Right? What should, because now you have several orbits, so you have a complicated interaction which is defined for each orbit, and then interactions between particles in different orbits. So this is a complicated interaction. He derives the conditions from this. What does it mean? They're very complicated. So I don't have a feeling of what this double commutator actually means. It's a mathematical derivation, but at least to me, maybe some people have studied this better than me, but this, yes.
So even if it's foggy, what it means intuitively, can we get some sort of sense of how strong this requirement is? Like, is this something that is very rare and nearly useless, or is this something that is seen often?
I would say the approximation is used frequently in the sense that you will assume a condensate, even if your Hamiltonian is not a pairing Hamiltonian, right, and deviates strongly from it, you assume that you can have a ground state of this type, right, where the alphas you might get it from a two-particle problem. You might say, well, I'm doing a minimization of my Hamiltonian. I have a state like that. This is a bit more general. This I can put as minus here. And minus 2. Right, and then I minimize with respect to the alphas. Right. This would be exactly the same if n equals 2 for two particles. This is an eigenvalue problem. Here it is a minimization problem. Right? And this is frequently done, but I have to admit, people usually don't check whether this condition is satisfied. So then it is an approximation.
Maybe there's some sort of connection between how badly this double commutator is broken to how quick convergence happens or something like that.
Certainly there will be a connection, but as I said, these lead to very complicated equations which I never had an intuitive understanding.
So what do you mean by generalization of seniority in that case?
Oh, because you have still this structure, right? This was sort of the hallmark of the seniority scheme, that in the ground state, right, this is for the ground state, but in the ground state you could write your ground state as n over 2 identical pairs. And this is very similar to that, except that now it's not just a summation with coefficients 1, but it's
Do you know, can we talk about what was the motivating factor for going in this direction from the seniority scheme? Like, why is this something that
I'm not telling me, yeah? So
beyond pretty
Darby
much?
was somebody who, well, is somebody, I should say, is somebody who had very much an algebraic approach to things. And he derived formulas, and then people asked what they mean, but okay. I don't know why he would. I think he must have realized the importance of this kind of formula in the usual pairing case, right, with the general orbits, and then said, well, can I derive a condition that comes back to this, right, but is more general? Because you see, the generalization is the fact that you can have probabilities like PCS probabilities, so you have orbits which are more occupied than other orbits. This is completely compatible with the scheme.
So this big delta is, capital delta is pairing up, or what is it?
That's a good question, but I'm not sure. Yeah, I'm not sure. It would seem so. I'm not sure. Yeah, I have to check to go to the paper. Maybe he discusses it. Yeah, that's a good question. Okay.
So, sorry to keep hammering this.
Yes, yes.
Well, what happens to the limit as delta goes to 0? Do we get a structure that we're familiar with again?
The only thing I can say is n is 0. So then it's sort of like n non-interacting pairs. So the delta must have something to do with interactions between the pairs. Interactions between pairs, I would think, are repulsive. Okay. It's something I have to admit I never understood very well the connection with this and with the Richardson scheme. Because this is more general in the sense, because you don't restrict yourself to a pairing Hamiltonian. Right? You have a more general Hamiltonian, but you get an eigenstate, at least for the ground state, which satisfies a property of the pairing Hamiltonian, which the Richardson Hamiltonian does not have. So I think this connection is not being, well, at least to me, I don't fully understand.
Okay, can I ask maybe about this Richardson, like about this wave function? How it is connected to BCS function? Because it's it looks like familiar.
Yes,
Similar.
it is familiar. This, in one sense, it has good particle number. This thing has good particle number, so there is no approximation with respect to particle number, because each of them is 2 particles and you sum, so you have an exact particle number. So then you would think, it's projected BCS, but even that is not true. Because projected BCS will be projected from a state which is like this, with identical structure. And so this is a further refinement on projected BCS. Okay, so let me, I think I finished with this is basically done. I have an example, but let me go over that. not say anything about neutron proton pairing, as we discussed by Augusto. So I now, in the remaining 45 minutes or so, I would like now to come to the second here, which is quadrupole. So Elliott's esoteric scheme. I'll try to explain that. So I repeat here. So you have this was what I call Pullman's Hartree-Fock, so a very simple harmonic oscillator Hamiltonian augmented with added to it a spin orbit and a orbit term, and then two-body. We saw this can be solved easily in that zero. Then I discussed a little bit if this two-body interaction is the pairing interaction in a single J-shell and J-shells. Right? So now I will come to when this two-body interaction is a quadrupole interaction and how you can find analytic solutions in that case. So, to do so, I first have to introduce a very old idea which is due to Wigner, and this is known as the supermultiplet model. Or alternative as the SU4. So what Wigner, this was Wigner in 1937. Okay, what Wigner assumed was a Hamiltonian. We get back to symmetries now. Suppose you have a Hamiltonian and it commutes with spin operators. So this is S is the spin. Okay, we're back to spin and isospin. It commutes with the isospin operators of TU, and it commutes with some operators which these are double tensors, they have two indices, and we will explain what they are in a moment. So SU, this is the spin, right? So it's we call, so you go from 1 to A, sum of all the particles of SU. Okay, same thing for the isospin. So this I discussed at length. I was reviewing isospin, and then this Y. So this is now, you can guess what it is. It's a sum of all the particles, and when an S mu spin, and then a T mu all the particles. Okay. This is, I sometimes call this Gamow-Teller operators, because a Gamow-Teller transition is a transition where you go from neutron to proton or vice versa, and you change the spin. And so this is an operator that can do that. Okay? And so what Wigner assumed is these commutation relations to be valid. Okay? You will see that's not really the case, but let's accept this and see what are the consequences. Well, so you must have states which are labeled by S, right, the total spin. have states which are labeled by T, the total isospin. Okay, as a consequence, and this is a bit less obvious, but of course you have rotational invariance also of the Hamiltonian, and so your Hamiltonian will be labeled by total orbital angular momentum L. Okay, one thing I forgot to say, you have now a collection of operators, S mu, T mu, and Y mu. These are three, you have three components here, 9, so that's 15, and actually you can show that this is an SU4 algebra. Okay. Of course, you have the usual scheme, so you have SU4, and the one which we know already from previous discussion is the algebra associated with spin, so that will be an SU2 spin algebra, and maybe an SU2 associated with the isospin, which we also discussed. Okay. So you have some labels, and the label of course is S, the spin, and the label here is T, and you have some labels here, and that is the difficult thing about super multiplex scheme. These are traditionally, apologize, but I will. These are traditionally labeled as lambda mu mu, and unfortunately I have taken here mu and mu. This has nothing to do with these labels. I'm not going to change. But this is the traditional way of labeling representations of SU. Okay, so now I'm not going to develop this in detail, the group theory of it. I would like to give you an idea. I mean, we know what this is, right? This is just the total copy. Yes?
Excuse me, sorry, because I didn't get it. Could you tell once more why it's SU4?
Oh, because this is 3 operators, this is 3 operators, these are 9 operators. You have 3 components here, 3 components here. So that's 3 plus 3 plus is 15. This is a poor proof, right? You just count the generators, it's 15. The number of generators of, let me write this here, it's not so important. This is the number of generators.
Squared minus 1, okay, yeah.
And for S, you just subtract the number of operators, so it's omega squared minus 1. If you wish, I could have added here the number operator, or whatever I call it, n, little n, okay? The number operator, if I add it here, then I have it. So please do not confuse lambda mu mu here, which are labels associated with SU4, with these components, which in my notes I need the same thing. Okay, so now we understand S, right? This is the coupling of all the spins. We hopefully understand isospin. That's a bit more complicated, but we will have an exercise on this kind of business this afternoon. Okay. What about these guys? What is the meaning of these labels? That is more tricky to understand, and it goes back to something which was discussed in detail by Rick, and I will repeat more or less what he said. What I will do is the simplest thing, non-trivial thing possible. I will look at 2 particles, 2 nucleons, in a P shell. Now I clearly say two nucleons. They might be identical, they might be one neutron and one proton. Okay, both cases are covered. And I want to do something simple, namely I consider a delta interaction, an attractive delta interaction between the two nucleons. Okay. One thing I would like to make, so this problem, so you would have, the usual way of thinking, you would have a P3 halves, and a P1 half, and then you can put a neutron here and a proton there, or vice versa. So you think, well, with lots of possibilities, how do I work that out? This afternoon we will work it out in this way, but let me work it out in a simple way. I know this interaction, it does not depend on S, the spin, it's spin independent and it's isospin independent. Okay? So I can decouple the spin, isospin part from whatever orbitally happens. What happens orbitally? I have to couple two particles in the P shell, and so, okay, how can I do that? So P, that means L equals 1, so P squared, it means I can couple to total orbital angular momentum 0, 1, 2. Right? I haven't said anything about antisymmetry yet. Okay? So now I know this for the delta interaction will be the most attractive, so let me say something here. So this will be this. I think I will put here S and here M. Okay. I will have, of course, I can couple the spins for each particle is 1/2, so I can couple to S equals 0. Let me do it here. S equals 0 or 1, and then T equals 0 or 1. The isospins, same thing. Then remember the rule. This must be odd. This is something we derived in the first lecture. Because of antisymmetry, this, if L is even, then S plus T must be odd. Okay? So this is the rule of antisymmetry. So now we can come to the classification. Let's put here T equals 0 and here T equals 1. Okay? Then here, if L equals 0, S must be 1. And then L equals 2, S must be 1. And then L equals 1, this is possible as 1. Then S must be 0. Oh, I have a mistake. So here the same thing, S and L. So here is S must be 0. Zero. Here, this is 2, 0. This is 1. Okay. Then I have to work out what are the J's. The J's are the coupling of S and L, so it's a 1 plus. Here, coupling is 1 plus, 2 plus, 3 plus. And here, the coupling of this one is 1 plus. Here, the coupling of S and L 0 plus, 2 plus, and this is 2, 0. That's fine. But it's correct. Yes. So, I've worked out the spectrum without doing any calculation, just by sort of thinking. So it should be. Yes.
But do you know the order of
Yes.
the
The further, there is one thing I don't know, but this one I do know. Because, you see, S plus T is even. L is odd, it means spatial part of the wave function is antisymmetric. I take a delta interaction. This is the argument Rick explained 2 weeks ago, or almost 2 weeks ago. Not 2 weeks ago. Rick explained this, that the interaction in a state which is spatially antisymmetric is zero. So without doing any calculation, I know that this is zero. These levels are at zero energy. And actually this afternoon we will prove that this is the case. Okay? The only thing, then I know, of course, the 0 plus is more attractive for the delta interaction than the 2 plus. Right? But this one, this difference here, is delta, I don't know without doing an actual calculation. But the important part is actually contained here. This is spatially, so we have spatial symmetry for all of those states. Here we have spatial antisymmetry. Actually, now we will remember the SU4 labels. Yes, I think I do. The point is that these SU4 labels are different for the states here than they are for the states here. Okay? And so the idea that I would like to get across is that these labels here for SU4, they tell you something about, of course, the total wave function must be antisymmetric. That's a requirement. But then SU4 tells you where do you put the antisymmetry. Do you put it in the spin, isospin part of the wave function, or do you put it in the spatial part of the wave function? And a reasonable nuclear interaction will try to put the wave function in the spatially symmetric state. So those are favored. These are, sometimes this is called favored SU4 representation. Or irrep, I should say. Okay. Is this sort of acceptable to people? The other point I wish to make is the following. That you see here, if you do, and this we will also show this afternoon, you see here, so this is basically a non-odd nucleus, so you have one neutron and one proton fission, and you see that you have one plus state, which is t plus 0, and it is degenerate with a 0 plus state, which is t plus 1. So the first order situation of a neutron and a proton is a degenerate 1 plus state, well, a 1 plus state which is degenerate with a 0 plus state. You will see, of course, this is not true, right? You will see an example where these are shifted, and we will try to understand what are the shifts. And also these levels here, you see they are degenerate in energy, and in an actual spectrum they will not be degenerate, but they will tell you something about spin orbit splitting and about the relative strengths of interactions in the t plus 0 and t plus 1. Okay. So are there questions on that? So what has this to do with SU3? So we will come back this afternoon just to this kind of situation. And some of the projects are also related to calculation of this type. Okay, so now let's do this a little bit more formally. So let's assume we have an entire oscillator shell, P shell, but it can be the SD shell, it can be the PF shell, and so on. And so the degeneracy of this oscillator shell is U4 omega. Okay, how do I count? The omega would be, for instance, for the P shell, omega is 1. It's 3. So it's 2L plus 1. For the SD shell, omega is 6, and so on. Okay? And the 4, it comes from the fact that you have 2 spin states and 2 isospin states. Right? Proton, neutron, spin off, spin out. Okay. So now, this business of SU4, actually it comes down to relating this. I have to this. Let me first SU4. As we saw, this can be reduced to spin isospin. Okay, we know what all of those are. Spin, isospin, these are the super multiplet labels, which we have some kind of a feeling. So this is the spin isospin part of the algebra. And so now I just will multiply with the orbital part of the algebra. And what do we want to have? We want to have a classification where we come down to SO3 associated with the orbital angular momentum. This is T. The labels here actually they are the same as those labels, somewhat transposed. And so what we did so far was look at this classification in terms of spin, isospin, and symmetry and antisymmetry. And so what Elliot claimed is that actually the orbital classification can also be specified, and we can always put here an SO3 group, which unfortunately usually is also labeled by lambda mu. Maybe I should change this. Okay, fine. Okay, so to what of a Hamiltonian does it correspond? So we have our H here. Actually, we take the kinetic energy. We have the harmonic oscillator. Plus or minus, I don't know. I will take a two-body interaction, Q. We can go to a second quantization, so this is so we can write it like that, h bar omega times, we consider an entire harmonic oscillator shell, so P is D, F, etc. And here we get sine
Shall everybody know everybody know more or less got this, I think, so this I don't need to explain. This was just to make clear that the basis used by this program is the significant basis. So this is what we're going to. The second one,
most of you also got this, although this was a bit lengthy because you had to put all those correct coefficients, Gordon coefficients. But there is one point which was essential, which was very important, in which I would like to emphasize. Yesterday, I told you that if you have a pairing interaction, the ground state of a pairing interaction can be written like this. Okay, where this S plus, it creates a pair of particles coupled to zero. What this exercise showed that the delta interaction also conserves seniority, and no, it's okay. It also conserves seniority, and you have now a spectrum where you have a 0 plus. This 0 plus, it has seniority 0, and it cannot mix with other states. And that means if you take a delta interaction, which is a very much more realistic interaction, the ground state has also the same structure. It is exactly the same structure, right? And this was found by several people. So that if you looked at the decomposition of the ground state of the eigenstate of a delta interaction, it had also a pure character in Hart model, which means that the ground state is seniority 0. If you look at odd mass nuclei, so this was for J equals 13.5, J equals 13.5. For an odd mass nucleus, the ground state has seniority 1. Okay, so the J, the angular momentum, is 13.5, and it is pure. It is also exact seniority. It has the same structure as you would get from a pairing interaction. So you had another 13 plus state with seniority 3, which was single. It did not mix with seniority 1. It does not mix with seniority 5, so it's a pure state. That doesn't mean that the delta interaction is solvable. There are many states that you cannot give an analytic expression for it, but you have a subset of states, like the ground state for the nucleus, the ground state of an object, which are solvable and which have a well-defined structure. So that's a topic. So that was sort of the objective of that exercise. Okay. Let me then go to this question about seniority isomers. This was about extracting interactions from two particle nuclei. So this is nickel 70. So nickel 70. So this is 28. 22, you consider this to be a closed shell. And so this then is a two-particle spectrum, and the two-particle spectrum, this is an approximation. The two-particle spectrum defines your matrix element. And the same thing for, what was it, molybdenum 92, right, which is 40 to 50. So this is closed in the neutrons, and then you have two protons in the G9. So you extract all the matrix elements from the data, okay, and then the objective was to look at the gauge properties. Here they are, so it's a little table, and in particular of the 8 plus, because the question was you have 8 pluses, right? In nickel 72, so that's a 4-particle nucleus, so it's 4 particles, 4 neutrons in the G9 half. This state is not isomeric. On the other hand, in ruthenium 94, so this is 4 protons in the G9 half, this 8 plus is isomeric. What is the reason? So you have defined the interaction from the 2-particle nuclei, and then you look at the energy of the 8 plus and what are the 6 pluses, because the main decay will be by E to B. And so you see there is here a 6 plus which is below the 8 plus, but the B2 is very high. So this you could calculate by looking at E2 transitions. Okay? But here there is another 6 plus, which is below the 8 plus with a very large P2. And so the transition here will be mainly to this second, the calculated second 6 plus, and so it will be a fast transition. On the other hand, in ruthenium 94, you see there is the 8 plus, one 6 plus is below it, but with a very small B2, and the other one is above it with a large B2, so the decay can only go to the first 6 plus, so that is why this state is isomeric. This is a very simple analysis which you can do just by looking at the 2 particle spectra and then predicting something about 4 particle spectra. You can do the same analysis, for instance, for lead isotopes. We discussed a lot about 10, 210, so it's 82 and 128. So this is also 2 neutrons in the G9 half, the second G9 half. So then you can predict properties, for instance, isomeric properties of lead-212 and lead-240. And you can easily convince yourself, taking the interaction here, that there should be isomers in lead-12 and lead-240. Okay. Last question. This was about SU4 symmetry. So this, first of all, this was an exercise in isospin. So you have to figure out what. So this is putting 2 nucleons in the P1 half and in the P shell, let's call it. So the P1 half and P3 half. So I did this exercise in the morning in terms of LS coupling. Here it's the same kind of problem, but now you do it in JJ coupling, so you should get the same result. And the result is shown here. Let me draw it because this is a little difficult to see. So you have T equals 0 states, T equals 1 states. At T equals 1, there is a 0 plus. Then there is a 2 plus. Here the energy is -3 in units of the strength of the interaction. The energy of the 2 plus here is minus, I found -6/4. And then there is a final state with T equals 1, is this one, which is at 0. Okay. Then we look at the T equals 0 states. What states do you have? So you have a state of -3, which is J equals 1, so that's a 1 plus. Okay. Then there is a multiplet. Here, at -6/4. These come from the diagonalization of these matrices if necessary. Right? So that is a multiplet which is 1, 2, and 3. 1 plus, 2 plus, 3 plus, at exactly the same energy as the 2 plus equals 1. And then there is one state, I believe, 0, which is 1 plus. Okay. So this is precisely the spectrum we obtained from LS coupling. You get the same result, JJ coupling. And you see the degeneracies, right? The 0 plus T equals 1 is exactly degenerate with the 1 plus T equals 0. So that's a consequence of the SU4 symmetry, all the degeneracies here. Okay. Now this is very schematic. So this is sort of the delta interaction. It commutes with spin, it's spin independent, it's isospin independent, and so that's why you see the degeneracies here of T equals 0 and T equals 1 state. Whenever you see these degeneracies in O dot n equals Z nuclei, this is a sort of a remnant of Now, the last thing I want to say, and this probably, this was not time enough to do this, but let me sketch you what is the relation with data. If you now look, so this is just one neutron and one proton, or two nucleons in the P shell. If you look at the spectrum of lithium-6, well, what I then asked, let's now introduce a delta epsilon, right? And this is a splitting between the single particle energy of the P1 half minus the single particle energy of the P3 half, because we know that you have some splitting, right? Then the only thing you have to do is put in delta, because in this basis this will add a diagonal contribution, a contribution to the diagonals, which can be either delta epsilon or twice delta epsilon or 0. Okay? And so then you can diagonalize the matrices, and now you look at what are the properties of the spectrum. You will find two things as a function of delta epsilon. Right? You can look at the relative energies of the 0 plus versus the 1 plus. What you will find is something like that. This is the excitation energy of the 1 plus, or the, let's call it the energy of the 1 plus. Minus the energy of the 0 plus. Okay? So if you introduce a spin-orbit splitting, you find that the 1 plus is always above the 0 plus. Which is a little annoying, because if you look at the data, then the data in lithium-6, for instance, it gives us a ground state, a 1 plus, and the T equals 1, 0 plus is at about 3.5 energy. Okay? So you cannot explain with the spin-orbit splitting, you cannot explain the relative energies of those two. Then you look at the second effect, and this is the splitting of this multiplet. Right? This multiplet is seen actually in lithium-6, and so the multiplet is 3 plus, 2 plus, 1 plus, add some energies which, well, they're given in the solution. So the ground state is a 1 plus, a 0, then the 3 plus is at 2.2 MeV, the 2 plus is at 4.3 MeV, and the 1 plus is at 5.6 MeV, and then you have T equals 0 states, and there is a 0 plus, so these are T equals 0, sorry, these are T equals 1, and there's a 0 and a 2 plus at 5.3 actually. 3.6. Okay, so you see the splitting here of this multiplet, it's 3 plus 2 plus 1 plus. And if you study that as a function of this splitting, you will see that the appropriate delta is positive. That means that the energy of the P1 half, the single particle energy, should be above P3 half. Okay. So from the spectrum of lithium-6, you can actually deduce two things. First of all, the splitting. The P1 half should be above the P3 halves. And secondly, the strength of the delta interaction in the T equals 0 channel should be stronger than the strength of the delta interaction in the T equals 1 channel. Only with those two ingredients you can get a spectrum where the splitting of this multiplet is correct. And the splitting between the 1 plus and the 0 plus state is correct, namely the t equals 1 is above the t equals 0.
So this is a simple example of how you can sort of extract essential information or good information about the nuclear-nuclear interaction from data with a simple. Are there any questions about this? Or this is all clear?
Can you add isospin term in the mean field?
If you want to include a Coulomb contribution, this can be done, yes. And this would then, you see here I have not said anything about what is the precise nucleus, right? These are all the states in lithium-6, right? If I would go to helium-6, of course I would not have the t equals 0 states, I would only have the t equals 1 state. Right? So you will only see this part of the spectrum, like in this approximation. Then if you add a Coulomb, you would add shifts. And I guess you would add, you would have some mixing, and the mixing would be between those two pluses. That's actually not so uninteresting because they are not so far apart in energy, right? So this is, in first approximation, this is